This is lecture 6, part 2, for space requirements and layout. This is for IE 4355, facilities planning. This lecture is a continuation from the first part, in which we discuss multiple things related to the designs of facilities. In this particular lecture, we're going to focus on some additional elements. So in terms of the course objectives, this particular lecture is going to be associated to objective number 4, which states that we should be able to design layouts incorporating product, process, and personal requirements. So as I mentioned already, there's a continuation of the first part of this lecture, in which we cover some space requirements and layout ideas for structural system performance, enclosure systems, and atmospheric systems. In this lecture, we are going to focus on the electrical unlining system and also the life safety systems, which are the last two topics in this agenda. In terms of the learning objectives, we want to provide an overview of how the system's elements impact the overall process of facilities planning. We also want to provide an understanding of the various system elements within the facility, not to prepare the facilities plan to design a structure or its heating, ventilation, and air conditioning or other systems, but to have an understanding of how those systems impact the design of your facility. And if you are designing a new facility, you need to have a discussion with the experts, let's say on heating, ventilation, then you can provide the details needed for the goals that you want to achieve for your facilities design. So in this lecture, we're going to start with the electrical and lighting systems. The facilities planner's responsibility is to specify what level of service is required and where it is required. The power company needs the electrical load requirement for a facility before construction begins. Requires a facilities planner to have a good preliminary estimate. So you as a facilities planner should know, okay, we're gonna need this much illumination, this is the type of equipment that we are going to have in the facility, and using, this is the type of HVAC system that we need to keep the temperature under control, and so on. So using that information, you should have at least a preliminary estimate on the electrical load for the facility that you're designing. The facilities planner must ensure that major load requirements, both present and future, are included in the design data. So the reason we're stating this is maybe you're working with a company, a startup, or a company that has a trend of growth. So you want to make sure that when you're designing this facility that you have the ability to expand your business. So these low requirements in terms of electrical systems, you have to take into account the current need, but also any future need for your company. Like if you plan to expand in terms of adding a second production line, or if business goes well, maybe we need more space for a warehouse and so on. So using this information, the design engineer can adequately size main switchgear, transformers, feeders, panel boards, and circuits to handle the future electrical needs of the facility. Table 1 has the average load requirements depending on a building type. So if we look at plants, we requires in terms of load 20 watts per square feet. Office buildings, 15 watts per square feet. Hospitals, since they need equipment, and for most of their rooms, they have a larger requirement, which is 3,000. Schools, 3 to 7 watts per feet square, and shopping centers about 3 to 10. So facilities lighting should not be planned by the same person planning the electrical services, because illumination should be custom designed for the areas within the facility. So if you're gonna have some people doing manual labor, you wanna make sure that they have enough lighting to be able to perform those operations. If you have people in offices, same thing. So it has to be custom designed for the areas. Lighting system may be designed using the following 8-step procedure. Step 1, determine the level of illumination. The minimum levels of illumination for a specific task are given in Table 2. When selecting the level of illumination for a particular workstation, the following criteria must be considered: the nature of the task, the amount of reflectivity of the workstation, components, and surrounding areas, the current level of natural or general lighting, the need for natural illumination, and the worker's age and visual acuity. So this is Table 2 that states the minimum illumination levels for specific visual tasks. So in the left side of this table, we have the different tasks. So they are trying to group the more general tasks that are associated with industrial facilities. And then on the right, second column, you see the minimum illumination level in terms of foot candles. So for instance, if we look at the inspection, if you're trying to decide how much illumination you need for an inspection task, then there are multiple levels: ordinary, difficult, highly difficult, very difficult, and most difficult. And you can state, or you can use these guidelines to state the level of illumination that you will need. Same thing for offices. So depending on the type of labor that you're performing in that office, then you can decide, or you can find the level of illumination that will be needed. If you're looking at paint shops, if you're looking at storage rooms and warehouses, welding areas, material handling, machine shop, assembly, and so on. So that's step 1. Step 2 is to determine the room cavity ratio, which is RZR. The room cavity ratio is an index of the shape of a room to be light. The higher and narrow a room, the larger this RCR, and the more illumination needed to achieve the required level of lighting. The RCR may be calculated using equation 1, which is taking into account the height from the working surface to the luminaries, the room length, the room width, and also again the room length and the room width. Step 3 is to determine the ceiling cavity ratio. If luminaries are ceiling mounted or recessed into the ceiling, then the reflective property of the ceiling will not be impacted by the luminaries mounting height. So the CCR need not to be considered. The greater the distance from the luminaries to the ceiling, the greater be the CCR and the reduction in ceiling reflectance. The CCR may be calculated using equation 2. So CCR is taking into account the height from luminaries to ceiling, the RCR, which was computed in step number 2, and the height from the working surface to the luminaries. And again, if the luminaries are ceiling mount or recessed into the ceiling, then there's no need for you to consider the CCR. Step 4 is to determine the wall reflection, WR, and the effective ceiling reflectance, ECR. The wall reflection and a base ceiling reflectance, BCR, value can be obtained from table 3. Okay, so here's table 3, which has the approximate reflectance and depending on the materials. So if you have white paint, light color paint, then the approximate reflectance is about 80%. If you have black paint, 5%, brick, cement, and concrete, about 35%. If the luminaries are to be ceiling mounted or recessing to the ceiling, the ECR is equal to the BCR. Okay, so BCR, sorry, the base ceiling reflectance. So these two will be the same if the luminaries are to be ceiling mounted. If the luminaries are to be suspended, the ECR is determined from the CCR, WR, and BCR using table 4. So we'll need these 3 values, WR and BCR, in order to compute the ECR. So the CCR was computed here in the third step, and the WR is coming from table 3. And so to determine the wall reflection, WR, and the effective ceiling reflectance, ECR, the WR and the base ceiling reflectance value can be obtained from table 9.6. So that's in your textbook. If the luminaries are to be ceiling mounted or recessed into the ceiling, the ECR is equal to the BCR. So in this lecture, if you go to table 9.6 in your book, you'll find the same thing as table 3 in this lecture. If the luminaries are to be ceiling mounted or recessed into the ceiling, the ECR is equal to the BCR. And if the luminaries are to be suspended, the ECR is determined from the CCR, WR, and BCR using table 4, which is shown in this slide. So the BCR value is here at the top. So you have to look at the values here at the top. And the CCR is listed here. And then WR is going to change depending. So if your BCR is 80 and your CCR is 0.5, then you're going to use this row here to determine based on your WR, which is 80, 65, 50, 35, 10, what will be the value. So these are values that if you get any number in between the values tabulated in the table, then you will have to use some interpolation to estimate the values in between. So the ECR is computed using table 4, the effective ceiling reflectance. Step 5, to determine the coefficient of utilization. The coefficient of utilization is the ratio of lumens reaching the work plane to those emitted by the lamp. It is a function of the luminaries used, the RCR, the WR, and the ECR. The coefficient of utilization for standard luminaries is given in table 4. And again, we have to use these parameters that we computed already to get to these numbers. And it will depend on the type of luminary that you have in your facility. So it could be fluorescent, it could be high intensity discharge lamps, or filament reflector lamps. So depending on the type of luminary and the spacing not to exceed, then using these parameters, you would determine the coefficient of utilization. So as you can see, in order to get these values, we have to use multiple tables depending on the step. Step 6 is to determine the light loss factor, LLF. The two most significant light loss factors are lamp lumen depreciation and luminary dirt depreciation. Lamp lumen depreciation is the gradual reduction in lumen output over the life of the lamp. Typically, lamp lumen depreciation factors are expressed as a ratio of the lumen output of the lamp at 70% of rated life to the initial value. The lumen output for various lamps given in Table 6 include the lamp lumen depreciation, therefore no additional considerations is needed. Luminary dirt depreciation is the light loss associated with the conditions under which the luminary operates. The luminary dirt depreciation varies with conditions and the length of time between cleanings. So here's Table 6 that state the lamp output at 70% of rated life. And in the first column, we have the lamp type, which includes the filament, the high intensity discharge, and fluorescent. And the second column, depending on the lamp type, we have the watts for each one of the lamp. And then on the third column, we have the lamp output at 70% of rated life. Table 7 has the lamp luminary dirt depreciation factors. So we have at the top the dirt or the condition. So it depends on the type of environment. Like for example, in the first type of environment, we have clean office light assembly or inspection, and we have the month between cleanings. And depending on those ratios of cleaning, we can determine the dirt depreciation factors. So if you're cleaning your lights every 6 months and you have a high intensity discharge lamp for a office, then this will be your dirt depreciation factor. Step 7 is to calculate the number of lamps and luminaries. We utilize equation 3 to calculate the number of lamps and equation 4 to calculate the number of luminaries. Okay, so the number of lamps is based on the required level of illumination, the area to be lit, and divided by CU, coefficient of utilization, and LIF, times the lamp output at 70% of rated life. The number of luminaries will be equal to the number of lamps divided by the lamps per luminaries. Step A will be to determine the location of the luminaries. So let's look at one example. In this example, we have a machine shop with 100 feet times 40 feet with a 13 feet ceiling. Will be illuminated for automatic machining and rough grinding. Uniform lighting is required throughout the machine shop. If the luminaries are to be ceiling mounted, all ceilings and walls are to be painted white, and all luminaries are to be cleaned every 24 months. What lighting should be specified? So let's look at this problem. Step 1 is to determine the level of illumination. And for that, we can use table 2 for automatic machining and rough grinding. So using table 2, we can find that level of foot candles. So let's look at table 2. Okay. So here we are going to be looking for automatic machining and rough grinding. So machine shop. If you look at this piece right here, is the description that we are looking for. And this states that we need 100 foot candles. So let's go back to the problem. So for this, we will need 800 foot candles. Level is required. Okay, step number 2 is to determine the room cavity ratio. So step 2, determine the room cavity ratio. And for this, we are going to assume that all working surfaces are 3 feet from the floor. So that's not stated as part of the problem. So we are making that assumption that all working surfaces are 3 feet from the floor. So we are going to compute the RCR. So the RCR is going to be equal to 5 times 13 feet minus 3 feet times 100 feet plus 40 feet divided by 100 feet times 40 feet. And that RCR is equal to 1.75. Step 3 is to determine the ceiling cavity ratio. Determine the ceiling cavity ratio. But in this case, the CCR need not to be considered because luminaries are ceiling mounted. Okay, so luminaries are ceiling mounted, so we don't need to consider the CCR. Step 4 is to determine the wall reflection. And the effective ceiling reflectance. And according to table 3, for this problem, W, R, and BCR are 80%. And because the luminaries are to be ceiling mounted, the ECR is also 80%. Step 5 is to determine the coefficient of utilization. So if fluorescent lamps in uncovered fixtures are to be utilized, the CR may be interpolated using table 5. As being between 0.88 and 0.78. Therefore, a CU of 0.8 will be utilized. Step 6 is to determine, go to the next slide. So step 6 is to determine the light loss factor for fluorescent lights with uncovered fixtures in a medium dirty environment that are cleaned every 24 months. A lamp luminary dirt depreciation factor of 0.85 may be obtained for table 7. So the LLF is equal to 0.85. Then step 7, finally, we can calculate the number of lamps and the number of lamps. So the number of lamps will be equal to this equation. So in this case, this is 100 times 100 times 40 divided by 0.8 times 0.85 times 3,300. And that is equal to 179 lamps. Okay, so using the discussion of this method, these 7 steps, and using the information from the tables, we can obtain or we can compute the number of lamps for a specified facility. Okay, the last piece of this lecture are a discussion on the life safety systems. Life safety systems are designed to control emergency situations that will disrupt normal operations. These emergencies are created primarily by fire, seismic events, power failure. Fire is the most pervasive of the 3 and accounts for the majority of costs associated with disaster. Fire resistance is therefore critical in the design of any facility. In terms of fire protection and safety, the first objective of the facilities planner is to determine the building's function and construction type as defined by the occupancy classification. These occupancy classifications are based on the International Building Code, and they are listed in this table. So group A up to U, and then the type are listed on the second column. The type of structure also governs the degree of fire resistance. Fire resistant, therefore, refers to the ability of a structure to act as a barrier that will not allow the fire to spread from its point of origin. There's no such thing as a fire immune building. Facilities planners must be cognizant of the need to provide for safety routes and an integral part of the layout. Most buildings require 2 or more exits. Most local building codes will require that maximum allowed time or distance to exit the building not be violated. No point can be more than 200 feet from an exit, 250 feet in a building with sprinkles, and up to 400 feet in a building with early suppression, fast response, fire protection, and automatic smoke and heat vents. So in this table, you're showing the maximum floor area allowance per occupant, depending on the type of building. So if it is an agricultural building, aircraft, assembly, gaming floors, assembly with fixed seats, and so on. And the use and also the floor area per occupant in feet squares. So 300 gross, 500 gross, and so on. The table 9.12 from your textbook shows the minimum number of exits for occupant load. So if there's 500 or more or less, we have a minimum of 2 exits. If we have between 501 and 1,000, a minimum of 3 exits, and over 1,004. In terms of the IVC remoteness requirement, 2 exits for exit access doorways, where 2 exits or exit access doorways are required from any point of the exit access. The exit doors or exit access doorways shall be placed a distance apart equal to not less than 1/2 of the length of the maximal overall diagonal dimension of the building or area to be served, measured in a straight line between exit doors or exit access doorways. Interlocking or scissor stairs shall be counted as 1 exit stairway. So as you can see, we, in addition to designing the facility for the purpose of the manufacturing and production, we also had to take into account the personnel, and we have to make sure that our facility is designed to accommodate the requirement of the pertinent agencies. So this is the end of the lecture. So in this lecture, we focus on the space requirements and layout requirements from a personal perspective, and also the impact of facilities design on and how to meet the needs of the people working in the facility when we are thinking about the facilities design. In this particular lecture, we'll focus on the electrical and lighting systems and also on the life safety systems.